Hi, and welcome to Mike Likes Robots, where we share knowledge to accelerate robotics. And today is day 24 of the advent of code, getting so close to finishing, and this challenge was maybe my most difficult one yet. I did arguably complete it, but I also arguably failed it, and I'll let you make your own mind up as I explain what I did. But let's go through it in order. We'll go through part 1 and my solution, which I did by myself. And then I'll go through the part 2 puzzle, and what I did to try and do the part 2 puzzle. But actually, I'm going to switch it up today. I'm going to show you my working code for part 2 first, and then I will explain how I tried to solve part 2. And then if you're not interested in the attempts at solving it, there'll be timestamps in the description so that you can skip to the end. So with that, let's take a read through part 1. Day 24, Crossed Wires. You and the historians arrive at the edge of a large grove somewhere in the jungle. After the last incident, the elves installed a small device that monitors the fruit. While the historians search the grove, one of them asks if you can take a look at the monitoring device. Apparently, it's been malfunctioning recently. The device seems to be trying to produce a number through some Boolean logic gates. Each gate has 2 inputs and 1 output. The gates all operate on values that are either true, 1, or false, 0. AND gates output 1 if both inputs are 1. If either input is 0, these gates output 0. OR gates output 1 if one or both inputs is 1. If both inputs are 0, these gates output 0. XOR gates output 1 if the inputs are different. If the inputs are the same, these gates output 0. Gates wait until both inputs are received before producing output. Wires can carry 0, 1, or no value at all. There are no loops. Once a gate has determined its output, the output will not change until the whole system is reset. Each wire is connected to at most one gate output, but can be connected to many gate inputs. Rather than risk getting shocked while tinkering with the live system, you write down all of the gate connections and initial wire values, your puzzle input, so you can consider them in relative safety. For example, here it gives x0 through 2 and y0 through 2, and then it gives z0 through 2 with a number of logic gates as examples. Because gates wait for input, some wires need to start with a value as inputs to the entire system. The first section specifies these values. For example, x00:1 means that the wire named x00 starts with the value 1, as if a gate is already outputting that value onto that wire. The second section lists all of the gates and the wires connected to them. For example, x00 and y00 goes to z00 describes an instance of an AND gate which has wires x0 and y0 connected to its inputs, and which will write its output to wire z0. In this example, simulating these gates eventually causes 0 to appear on z0, 0 to appear on z1, and 1 to appear on z2. Ultimately, the system is trying to produce a number by combining bits on all wires starting with z. Z0 is the least significant bit, then Z1, then Z2, and so on. In this example, the 3 output bits form the binary number 1000, which is equivalent to the decimal number 4. Here's a larger example. I'll skip over this. After waiting for values on all wires starting with Z, the wires in the system have the following values. And again, I'll skip past this. Combining the bits from all wires starting with Z produces the binary number, this. Converting this number to decimal produces 2024. Simulate the system of gates and wires. What decimal number does it output on the wires starting with Z? Your puzzle answer was a very large number. So I came into part 1 thinking nothing too challenging, quite interesting from my days of electronic engineering at university. Doing this kind of gate combination to make a digital adder was first year course stuff, so I was, well, that was a bit of a giveaway. The digital adder comes into part 2, but this kind of logic gate stuff I have done plenty of. So let's switch to the code and I'll show you my solution. Now the solution I'm showing on screen will be different to what I put into GitHub because there's a lot of functions and a lot of commented code here that I wanted to show you while recording, but is completely irrelevant to the actual solution. So I'm going to strip out everything that's not relevant when I actually commit it. And if you want to see how I worked through it, it's available here. So this bunch of comments was while I was trying to work out part 2, so we can skip past this and go straight to the parsing code for the crossed wires struct. So I decided to keep the puzzle input as a hash map of string to wire source, meaning the string is the wire name and the wire source is how it's calculated. There's 4 possibilities, the 3 gates, each of which has a string that it is referring to, and a const, which is just a number either 0 or 1, but I've defined it as U64 so that later on it's easier to do conversions. Then there's also an error value in case there's no wires or gates found or they're badly formed, which means that my fromString function works through the puzzle lines. For each one splits by the colon. Let me pull up the test text on the side so that I can show you it at the same time. So we have the wire number colon 1. So we can take the wire by splitting by colon and taking the 0th value. We can take the value by splitting by colon and taking the 1th value and then parsing it as a U64. And if either of these don't work, it outputs a badly formed wire, and then it inserts it into the wires hash map. So one thing here is that I managed to use the lines iterator. I tried to do this in an earlier puzzle, I can't remember which one, but I couldn't get it to work. I couldn't use one iterator. I ended up recreating the same iterator multiple times, which probably compiled to the same thing, but for the sake of my learning, I wanted to be able to do it. And I did manage to here. So at this point, it checks if there's any wires in the hash map. If there's not, it returns an error. Then it continues on, and it does for line in lines from there. So lines has already had some entries taken out up to the blank line, and then from here it parses by the logic gate, and it splits by white space, and then it expects particular values at particular points because they always have the same construction. So it starts with source 0, then it does the operation and XOR or, then it does source 1, we ignore the arrow and we take the result, which will be the gate that it outputs to. Then we're just matching against the operation and XOR or, and then matching against the particular wire source, and if any of those are unrecognized, then it returns badly formed gate instead. Then finally it checks whether there's an increase in the number of wires available, which means that some gates have been found at least. If there's not, it returns an error, and then it returns OK. So this parsing code will check that valid wires have formed and valid gates have formed before it returns OK from the fromString function. That's all it takes for the parsing of the code. Next, I went on to the value. Let me get rid of that test text now, we don't need it. And essentially, we are doing the value of a particular wire. So I defined the function here to find the value of a particular wire. It started from andSelf. So originally it read andSelf, and then for this I would do self.wires instead of the wires that is passed in. Now I changed that later on because for part B I wanted to be able to compute the value from a hash map which had been modified, and I didn't want to have to modify self to be able to do that. So instead I changed the function to be a static function which operated on the hash map that is passed in. That made it a lot easier to change the hash map and test the new values. Okay, so value returns value inner. Value inner is similar except that it contains a visited hash set. Originally, I didn't have this either, but again, for part B, I needed to be able to check if there were any loops. The puzzle input as it is doesn't loop one gate into another. That's not true if you start swapping things around and you're not careful about what you're swapping. So what I did here was check the visited gates as I go through them, and if any come up as having already been visited, then I return none. This isn't a valid value. Otherwise, it matches against the wire. None returns none. If that wire doesn't exist and it doesn't have a value, return none. Otherwise, return the value of the const, return or get the two values. For each of the 3 logic gates, the logic is similar. get the L and the R as the two string names of the wires, compute their values, and then combine them together. And that's by doing value inner on L and then. So if it returns none, we stop immediately. If it returns some, we go on to the next stage, which is computing the value of R. If R also has a value, then we can do the map. And the map says take R and return L and R. Or it can return L XOR R or L or R. And these are all bitwise operations corresponding to the gate. So at this point, I'm still trying to do everything nicely with options. Later on for part B, I do give up doing that. It became too much effort and I just started to unwrap everything. The truth is, for Advent of Code, you don't really need to deal with options. You can just unwrap everywhere and be unsafe, and it's fine because you're only running on inputs that the puzzle has given to you or you've defined. So it is perfectly reasonable to only operate on the same input and expect it to produce valid answers. I'm trying to use Advent of Code as a way to learn Rust better. And through this practice, I've gotten much better at dealing with options and results. So I tried to continue it at this point, but the puzzle got too complicated. We will get onto that. Okay, these are all helper functions that help with part B. Here we go, part A. So I have a helper function convert starting with, and that takes the wires and that start with Z. So let's look at this function. So convert starting with takes the hash map, the same wires hash map. Again, this could have been and self, but instead I passed in the hash map. I filter over the keys of the hash map to the ones that start with the particular character, in this case Z. Then I sort it so that it's Z0 through Z, the upper limit. Then I reverse that so that it's the maximum Z on the start of the vector and Z0 at the end of the vector. Then iterate over that. We can pass in wires. So we have an initial value of 0 because we are summing or even doing a bit shift to add each bit in. And then we take the accumulator, which starts at 0 and becomes bigger as we go, and the gate that we're trying to compute, which is actually the wire value. So then we get the value of the gate from the wires. So remember, if it's x0 here, then it's a constant that returns a value, either 0 or 1. If it's a gate, then it will recursively compute the values from that gate, and it will still return either 0 or 1, which is why this map at the end, it takes the value, either 0 or 1, and it bit shifts the accumulator left by 1 and adds the value, which will just insert the 1 or the 0 at the end. This also could have been an OR more correctly, but it produces the same answer because val is always 0 or 1. Then because this could produce an option that's unwrapped automatically by trifold, and then trifold will return the final option of U64, which is the value of the wires starting with Z. So running that is very, very quick and produces the correct answer. Let me go to main and I'll show you it running. Part A, none. That's unhelpful. Okay, that's something that I'll fix after the recording before I commit to GitHub. Something basic has changed in my code while trying to do part B. I'll figure out what it is. Suffice to say that my original version of part A did return the correct answer here. So with that, let's move on to part 2. So for part 2, after inspecting the monitoring device more closely, you determine that the system you're simulating is trying to add 2 binary numbers. Specifically, it is treating the bits on wires starting with X as one binary number, treating the bits on wires starting with Y as a second binary number, then attempting to add those 2 numbers together. The output of this operation is produced as a binary number on the wires starting with Z. In all 3 cases, wire 0 is the least significant bit, then 1, then 2, and so on. The initial value for the wires in your puzzle input represent just one instance of a pair of numbers that sum to the wrong value. Ultimately, any 2 binary numbers provided as input should be handled correctly. That is, for any combination of bits on wires starting with X and wires starting with Y, the sum of the two numbers those bits represent should be produced as a binary number on the wires starting with Z. For example, if you have an addition system with 4 X wires, 4 Y wires, and 5 Z wires, you should be able to supply any 4-bit number on the X wires, any 4-bit number on the Y numbers, and eventually find the sum of those two numbers as a 5-bit number on the Z wires. One of the many ways you can provide numbers to such a system would be to pass 1, 1 on the X wires, 11 on the X wires, which is 1, 0, 1, 1, and 13 on the Y wires, 1, 1, 0, 1. If the system were working correctly, then after all gates are finished processing, you should find 24, 11 plus 13, on the Z wires as 5-bit number 11000. Unfortunately, your actual system needs to add numbers with many more bits and therefore has many more wires. Based on forensic analysis of scuff marks and scratches on the device, you can tell that there are exactly 4 pairs of gates whose output wires have been swapped. A gate can only be in at most one such pair. No gate's output was swapped multiple times. For example, the system below is supposed to find the bitwise AND of the 6-bit number on X0 through 5 and 6-bit number on Y0 through 5, and then write the result as a 6-bit number on Z0 through Z5. However, in this example, 2 pairs of gates have had their output wires swapped, causing the system to produce wrong answers. The first pair of gates with swapped outputs is X0 and Y0 through Z5, and X5 and Y5 through Z0. The second pair of gates is X1 and Y1 to Z2, and X2 and Y2 to Z1. Correcting these 2 swaps results in the system that works as intended for any set of initial values on wires that start with X or Y. In this example, 2 pairs of gates have outputs that are involved in a swap. By sorting their output wires names and joining them with commas, the list of wires involved in swaps is Z0, 1, 2, and 5. Of course, your actual system is much more complex than this, and the gates that need their output swapped could be anywhere, not just attached to a wire starting with Z. If you were to determine that you need to swap output wires AAA through with EEE, 000 with Z99, and so on, your answer would be AAA something, BBB something, 000 something EEE. Oh, swap those 2 over. Your system of gates and wires has 4 pairs of gates which need their output wires swapped, 8 wires in total. Determine which 4 pairs of gates need their output swapped so that your system correctly performs addition. What do you get if you sort the names of the 8 wires involved in a swap and then join those with commas? Your puzzle answer was here. Okay, so my thoughts after initially reading part 2 was, what on earth? And that was pretty much my second and third thought as well. I had no initial idea on how to do this. Now, I did have a good plug at it, but as I said at the start of the video, what I'm going to do is show you what I did to get it working, and then I'll go back and I'll show you all my different attempts at trying to make it work that didn't pan out. I got nothing working, not even, well, technically one of them would work eventually, but it would have taken a long time. Okay, so let's take a look at the code, but also the source of the code. With my solutions, I tried a lot of different things. Eventually, I decided to look at either a hint or a full solution. Now, I did get a full solution for this, which I'll show you now. Here it is, this comment, and the link will be in the description. And it says, like so many others, I ended up rendering this in GraphViz and doing spot the difference troubleshooting. I tried unsuccessfully to reduce this to A*. Essentially, this person has given code which renders the entire system into a format that can be produced graphically that they can then look through, rather than trying to do it programmatically, as I had been trying so hard to do. And I think the final result is, to do this programmatically, you need to make a number of assumptions about the system that aren't in the puzzle text. For example, all Z wires are XOR gates. If you know that, then you can start to compute the result. So I think that what I was attempting to do wasn't even possible without having more rules in place, such as Z wires are XOR gates. So I took a look at the code. I was most interested in part 2. Their part 2 A* didn't work, which is why it has underscores. So the part 2 here, and I took all of this code and tried to understand it. And essentially what this code is doing is it is writing a .dot file, which is viewable with GraphViz. Now, if you want to do this, don't worry about downloading GraphViz. I found this tool, GraphViz Online, to be very suitable for doing it. So you don't need to install it yourself. You can write your own .dot file and plug it in here. But at this point, I'd given up trying to do it programmatically. I instead use this code as inspiration to create my own .dot writer. And at that point, I would say that I failed because I took a solution. But what I found was their solution doesn't actually match up with the puzzle inputs. I don't know why not. Maybe this person was very careful in obfuscating the wire names so that they're not just giving away the answer, which is very good of them if so, because it let me solve the puzzle for myself using the .dot file. So to WJ Holden, thank you for obfuscating your wire names if you did do that. That was a really nice touch that let me still do the problem for myself. And I would argue that I have done the problem for myself. I've used this code essentially as a guide on how to write .dot files. I did my own code for how to actually write the gates out and the wires out, and I did my own looking through the wires and figuring out what was wrong. So arguably, I have solved this problem not programmatically, with using a visualized graph and with using inspiration from this code to help me write that .dot file. So let's take a look at the code. Here we go. Here is my code, and it is similar to the code from the GitHub screen that I was just showing. Essentially, you create a day24.dot file, you use a buff writer to be able to write into it, and then it returns the results so that you can keep using question marks instead of checking the output of writeline every time. So what happens is I've already passed the puzzle, so I'm going to iterate through it. Each one I'll match the source. If it's constant, you don't put it in because you don't want a node to be an input. Instead, you can just create a node as the output of another node, and it will create a bubble for it. So const we ignore, and then AND, OR, and XOR have a similar setup, whereby the wire on the left has an arrow to the next node, and then again to the right node. So wire goes to the left, wire goes to the right. So imagine that you have a Z00, which is the AND of 0 or X0 and X1. That's not correct in the real puzzle, but take that as an example. So it would say Z0 to X0, Z0 to Y0. Then we'd also label that wire. So the label would be Z0, and it would have AND in brackets because this is an AND gate. Then I have the same for OR and XOR. But a further touch is that you can color the bubbles that are produced. So in this case, I've got AND gates in red, OR gates in blue, and XOR gates in green. So let me pause there and show you what that looks like in the GraphViz. Okay, so this is where we're starting, and now we're trying to do some visual debugging to figure out what's going on. Now, the nice part is that a digital adder has a pretty repeatable setup. That is to say, an output bit, let's say Z0 over here, or Z45. I'm sorry about the contrast. I didn't pick colors so that you could read the text easily. I'll have to tell you what they say a lot of the time. This Z gate is an OR between these two AND gates. That's at the end, which makes it a bit of a different setup. From then on, the setup is very similar. We have a Z, which is an XOR here, and it XORs the XOR of the two X and Y gates corresponding to it. So Z44 is XOR of something with the XOR of X44 and Y44. The other value being an OR. Now, the function of this is that if you pass in two zeros, you want a 0 out. If you want 0, 1, 0 plus 1 is 1, you want a 1 out. Same with 1 plus 0. Finally, 1 plus 1, you actually want 1, 0. So the bit you're looking at will actually be 0. So you need to account for the carry bit in the next level up. That's where this OR comes in. So each level, Z44, is the X and Y44 ORed with the carry from the previous level. And that's the essential, that's the basic structure. It just chains this logic together all the way down the tree, which means that when we look at this, we can figure out places that the logic has gone wrong. A lot of the places you can see this kind of format of top arrow, bottom arrow, and diagonals. Top arrow, bottom arrow, diagonals. Same again here, same again here. And this is where it starts to get a bit weird. X40 and Y40 are on their own. Now, this could just be that there's a difference in the way the graph is being shown on screen, but oftentimes it's because there is a wire or two wires that are out of place. So if we zoom out a bit, we can see there's a bit of a bubble there. And if we look further along, well, there are other bubbles, but they are hard to spot at this level. And I did spend some time zoomed in very close trying to figure out what the bubbles were. So let's go back into that one bubble. And because we're expecting the same pattern every time, we can check if that pattern exists. So for example, we know that this OR is always fed by two AND gates. This OR is fed by two AND gates. This OR is fed by two AND gates. This OR is fed by two AND gates. Chances are the ORs are not wrong in any way. We can also check the Z values. So the Z should be an XOR of an XOR with an OR. It is. It should be an XOR of an XOR with an OR. It is. And again here. Then we should have the OR should be fed by two ANDs, right? And then one AND is the two gates, which it is. And this AND is XOR and OR. This AND is XOR and OR. So I think in this case, it actually is the graph being rendered oddly. So here is an example of where it's gone wrong. And we can see immediately that there's a problem because we're in the middle. We should be getting XOR gates for every single Z value. Well, maybe not the ends, the far left and the far right, but in the middle, it should always be XOR gates. This is an OR gate, so we can immediately see that it's the wrong value. It's been switched somewhere. Now, the OR gate should be fed by two AND gates, like here, or it's fed by AND, or AND, I guess you should say. So this is the right OR gate. It's just been switched by something. So clearly there's an XOR gate, probably this HHH, which should have been swapped over. That if we swap those two over, then the Z20 will be the XOR of an XOR and an OR, which we would expect, and HHH would be the OR of the AND and the AND. And then we can see the previous AND gate points to it, so it should be the OR gate. So those two should be swapped over, Z20 and HHH. So what we can do, and what I did do, is I created a second version of the .dot file. Essentially, I'm doing exactly the same thing into a new file called day24 swapped, and I'm creating a closure that will swap two wires over from the wires hash map, right? So I clone the wires in self.wires, and then I use my swap closure to swap over different wires. Z20 and HHH need to be swapped. And then while I was debugging, I output it multiple times. I ran this and I took the swapped file. Let's do that quickly. Then if we zoom back in on the Z20, we can see that Z20 and HHH here have been swapped. And now the chain is looking correct again. We have these same clusters moving up and up and up. That's what I did. I did that 4 times to find 8 wires that needed to be swapped with each other. Each one, I added them into my swap functions, and then I modified my closure after the initial swapping in the hash map to also push into a vector. The idea being that I only need to hard code these wires once. Every time I do a swap of 2 wires, they both get pushed into the swapped wires vector. Then at the end, I can just return the sorted version of those swapped wires. So that's all that we do here. Once we've written the second file, is that we iterate through them, sort them, and join with the comma, and return that as a string. So that is part B complete. Now, this is very, very close to just hard coding the solution and returning it. So I'm not actually calculating the answer within this, but now that I've shown you my correct way of doing it, the way that I actually solved the problem, I'll take you through the ways that I tried and failed to solve the problem. So the first, which is perhaps the most obvious, is to try and iterate through all the possible 8 combinations of 8 wires and try swapping them over, seeing if the answer is now right, and if not, swapping them back. Or just using an immutable version where you clone it, change the wires, and then delete it if it's not correct. Either way, I chose to go with the swapping and then swapping back. And essentially what I have is the Z wires that I'm interested in, where I just filter over all my wires and see if they start with Z. I get my swappables, which is any wire that doesn't have... Oh, actually, that should be a not, I think. Okay, so that function was wrong anyway. Let's see if that runs now, just to try it out. Which I very much doubt it will, but I can leave that running down below while I carry on talking through the rest. So this is the kind of brute force check every possibility and see what comes out. Now, I did make an assumption. I wrote this code before I did the visualization. So I did make an assumption that X and Y, or rather anything with a const fed into it, isn't a valid wire to swap. And I was right on that, judging at least by the correct solution, which has no X or Y wires in here. It's all Z wires or gates in betweens. So that was fine. I had a swap function which swaps left and right in a given dictionary. Pretty simple. Get left, get right, insert right with right and left respectively. Then I did the X number by convert starting with X, the Y number by convert starting with Y. I've already talked through that function. It's how I solved part A. And then Z correct is X plus Y. Again, for this, I assumed that the initial input is enough to determine when all the bits are fixed correctly. And given that this function has never terminated for me, I can only assume that's right. I don't know. But then for each permutation in n permutations, this is itertools. And again, a really powerful thing. It's essentially for a vector, and you can give it a number of permutations that you want. So if I have, that seems like a really bad example. Oh, it doesn't take into account the equality of the iterated values. Fair enough. So if I have the range 5 to 8 and I want all the permutations of length 2, it'll give me 5, 6, 5, 7, 6, 5, 6, 7, 7, 5, 7, 6. You'll notice that it does give the different orders possible, so it can give 7, 5 and 5, 7. And also that there are more keys than in the permutations. So if I take all of my wires and I want 8 permutations, it will give me all the possible 8 combinations in all possible orders. So with that one function, I'm able to get all the possible permutations to check. For each one, I go through the chunks of 2 and swap them over because it's going to give me every order possible, right? I always assume that they're in pairs. So pair 1, pair 2, pair 3, pair 4. And I swap wire pair.next, wire pair.next. Then I test if they're correct by convert starting with X. That should be Z. That's 2 bugs in my code I found while trying to explain it. So let's stop that because that'll never terminate. Oh, option on wrap on a none value. Excellent. I think we'll give up trying to run that. That's just not working. So all I do is I do a test value, test the new value. It should be the Z correct value. And if it is, return that permutation, but sorted and joined with a comma. If you get through all the permutations, return none. So this function would correctly return none if there are no possible set of 8 permutations that will fix the code. I also pass in the number of permutations here so that this would work for the example AND gates that it gave. You would just pass in 4 permutations instead of 8 and it would eventually figure it out. I think that might even be how I got some test cases working right at the very bottom. Test AND's text, test part B text. I got it working using part B alt apparently. So I showed you alt4 first because I wanted to retry the brute force at the end after I'd failed everything else as one last attempt, just to see if running it for, a few minutes would end up working. But that was my initial attempt. I then went on to try and be a bit more clever. Now I'm going to speed up talking over this code. I'm going to try and talk through what my intentions were rather than what every line of code does, because I think there would be far too much to cover if I went through what every line does. So we're going to start with part B. Part B has a lot of commented code and a lot of me thinking about how to try and fix it. But essentially it gets all the Z wires and it expects the Z wires to have particular dependencies, XY dependencies. So this is me trying to use my knowledge of the digital adder to figure out what the Zs should be. So my assumption here was that Z0 should depend only on X and Y0. Z1 should depend on X1 and Y1, but also for that carry bit that I was talking about, it also needs to depend on X0 and Y0. And the same goes up. If we always do the expected XY dependencies, and we get all the possible sources recursively for a particular Z wire, and filter out only the X and Y ones, they're the only ones we're interested in, those should match up, right? Every time we go up a Z wire, we're increasing our dependencies. Z20 should be X20, Y20, X19, Y19, X18, Y18, because of the cascade of carry bits going down the tree. So that was my assumption. I figured that I could calculate the expected XY depths. I also tried to optimize it by figuring out at the very beginning, recursively, all the dependencies from a particular gate so that I can make the lookup quicker. I don't think that ended up helping, but I did it. And then XY depth is a closure that takes a wire and returns all of the XY dependencies. So it recursively searches from that gate and filters to just the XY dependencies. Is XY starts with X, starts with Y, and then I iterate over all the Z wires. For each one, I say that it depends on the next two values, X and Y, and then I try and fix it so that it does depend on those values. I thought this was essentially from there, it just tries all of the possible solutions. It tries swapping over all the wires under a Z gate until it produces the right dependencies. And I thought this was a pretty clever way of doing it, but I couldn't get it to work. And I tried it again, in fact. So part B and part B alt were the same thing, except that part B alt, which is here, is rewritten to look slightly nicer. It divides up the code a bit better into functions and so on, which are what all these functions in the middle are. X dependencies contains all net value. I also had a further optimization, which is that I realized that I don't need to check X and Y values because I assume that they're always the same, right? A gate depends on X and Y. So I only need to check X. I don't need to check Y as well. So I set it down to only check X values. And it does essentially the same thing, split up with functions so that it actually worked better. Now it was after writing this function that I tried it, and it worked for the AND gates, and I was pretty happy that I had a working solution from my unit test passing. So I ran it on the real code, and it immediately gave back nothing. Absolutely nothing. And when I looked into it, it is because all of the Z values in the real digital adder already only depend on the X dependencies they're meant to. I've not actually found a problem case where you can see a Z wire has been swapped. So Z4 already depends on only X4, Y4, X3, Y3, etc. So I couldn't use this to check that a Z wire was wrong. So I basically iterated over all the Z wires, found that they were all already correct, and then terminated the program. So that wasn't going to work. Moving on to part B alt 2, I started trying to do a different way of checking, which is that I would check for every bit, I would put in a few test cases. So I'd say that 0, 0 plus 1, 0 should be 1 on the Z bit. 1, 0 plus 0, 0 should be 1 on the Z bit because it's just adding 1 to 0. And then I also check carry cases. So this 1 comes from this left bit here, right? No carry cases because Z0 doesn't have any carries in it. I also have a set with only one bit on the left. Then I iterate over and I check, or I have a setcar function that allows me to set the X bus and the Y bus, and the test adder bit correct closure, which checks that for a particular index that the test cases pass. So either no carry cases if index is 0 or carry cases if the index is 1. Then I can set the bits on the bus and I can check whether the Z value is correct. Did this work? No, it did not. I found that swapping dependencies would make the test cases pass when it wasn't actually the right test case, or it wasn't actually the right wires to swap, which meant that when I ran it, Z2 would be broken. It would swap 2 wires that seemed to work, and then everything from then on would be broken as well, because the carry doesn't work anymore, right? So from there, it would eventually get to a wire which doesn't work at all, didn't find a swap to make it work, and it would terminate. So this just didn't work either. So I went on to Alt3. Instead of just checking the 2 bits on X, Y, X, Y, and checking the Z bit is correct, I went from the Z bit downwards. So I set up the X's and Y's so that it's all 0s and then all 1s, so that it's repeatable, which is a bad explanation. Basically, instead of just checking the 2 bits that feed directly into the Z bit calculates from everything downwards, so I should check the entire integer at once. So I set the entire X bus at once and the entire Y bus at once from the index to the end. And I thought this would work better and ran into exactly the same problem. The same problem being that there were multiple candidates that were available. So I swapped the first 2 thinking there would only be 1, and then it just broke. Then I tried adapting my code to track all of the candidates that could be swapped. And I got a lot of them, and I didn't have a good way of termination. I think that maybe this case would work eventually if I followed it through, where you go until you find a broken Z bit using the test case checker. Then you go until you find, at that point, you find all the possible swap candidates. Then you go to the Z bit and you check all of those swap candidates. And then you should be filtering down to fewer and fewer possibilities until there's only 2 wires to swap that makes it work. Unfortunately, I don't know if that would work. It might be that you get to another mistake while you're still filtering down wires. So maybe you just need to track all the possible swaps for all the possible Z wires. And at that point, you're just brute forcing it. Or you're very close to brute forcing it. So I did a lot of trying to do an intersection of saying, hey, Z3 has these swap candidates. Let's see which of them also existed for Z2 and only keep those ones. And I don't think I even made this function finish, let alone do something that worked. That is the point where I decided I had given this my all. I hadn't found a good solution. It was time to try and start visualizing it. And my first attempt to visualize it was to use this eGUI graph. So check this out if you ever want to use a graph UI in Rust. I didn't get this working, unfortunately. I couldn't make it compile. And I think it might be because it's Windows. I'm not sure, maybe the basic example doesn't work, but I didn't give it too much of a chance either. I would put this down to my fault rather than the crate being wrong. I probably didn't use the dependencies right or something. I basically copied their basic example, added the dependencies into my cargo toml and tried to run it, and it wouldn't compile. And at that point, I kind of gave up and went to look for a solution. That is when I found this Rust code that did the visualization. And from it, I learned how to write dot functions, dot files, and visualize them with GraphViz to be able to look at the insides. I've also learned from this that you don't always need a programmatic solution. You can go with some solution if there's a way to visualize it or a way to use maths to find it, as we had in day 13, I think it was. If you can get a solution, that's great. And if you want to solve it programmatically, you can still solve it mathematically or visually first to help you figure out how to do the programmatic version. And I think from reading through some of the other entries in the Advent of Code subreddit, that's what a lot of people did. They visualized it, they solved it visually, they realized what the rules were that would help them solve it programmatically, and then they wrote the programmatic solution. So I'm happy to leave this where it is. I don't feel the need to write a programmatic solution. I'm going to move on with day 24, complete and or fail, depending on whether you think I cheated or not, but I did learn from it. And that's what's most important and why I'm doing the challenge to begin with. So if you got this far, thank you for watching, and I'll see you next video for day 25.